Thank you very much. Can you hear me okay? Okay, good, because I'll just pretend there's 300 people in the room and pretend like I'm teaching. In any event, I'm going to talk today about precipitation. Usually temperature gets all of the action and everybody's interested in temperature. I spent most of my life working with precipitation, so therefore that's what I'm going to talk about. The interesting thing about measuring precipitation is it's a little bit different than every other variable. Every other variable we're trying to look at the impact it has on the energy or making things move. What we're looking at in precipitation is we're actually trying to collect mass. So it stands to reason then that a rain gauge probably doesn't need to be much more than a tin can and a dipstick. And in fact, you'll find that that's primarily what we have done for a long period of time. In second grade, when they start to teach people about meteorology, one of the things they do is they repurpose a 2-liter bottle and we have an impromptu rain gauge. And so, you know, you can make it pretty much out of anything. Sometimes they abuse the privilege, but nevertheless, the National Weather Service came up with the standard 8-inch rain gauge that they used for years and years. And if you look closely, I don't have a pointer, but you can see there's a dipstick. There's essentially a funnel. It is no different than a tin can with a dipstick associated with it. There's other ways of measuring it that we use from time to time, but they don't usually get into the widespread use. These are Belfort rain gauge or a Fisher-Porter rain gauge. These are based on measuring weight. So how much have we collected and we convert it by weight. This is a Gianor weighing gauge, which is an interesting design, which has a electronic string that goes down the side and you pluck the string and the frequency with which it vibrates tells us how much energy there is. You can see we have optical rain gauges, so as the water intercepts the line of sight between the emitter and the receiver, we can estimate the rainfall rate. We have hot plate precipitation gauges. The idea now is to take the one plate faced downward and one place faced upward. The one faced upward gets caught with rainfall and snowfall, and it has an additional demand in trying to evaporate the moisture, and so you can come up with a rainfall or snowfall rate that way. We have acoustic rain gauges because the sound of rain on plastic or the sound of snow on plastic somehow can be converted to rainfall intensity and frequency measurements. But most of them that we've found, and we've been taking measurements for years and years, really are nothing more than tin cans with a dipstick. Now, I'm going to go through a number of these as I talk because this is essentially the problem I had. I'm trying to put together a global climatology of precipitation. And you'll notice different countries use different gauges. Almost every country has their own design and their own concept, and they're at different heights. Some are buried partially in the ground, some are on stakes. Generally, the higher above ground they are, the more likely there is to be snow to keep them out of the snowdrift. And this is the problem. When you go across from one country boundary to the next, you get a discontinuity because it's one gauge over here, it's another gauge over here. They're measuring different things, and so they have different errors associated with them. I should have put a faster speed on this. In any event, there you go. And my favorite, the one from the Netherlands, because if it's not raining, it doubles as sort of a beer stein. The interesting thing about rain gauges is people think they're everywhere. They're not. They're only in places primarily where we have developed countries, and they're generally where people live. So you can see this is where developed people live, developed countries. Generally, that tends to be in lower altitudes. There's a lot of underrepresentation in higher altitudes. There's a lot of underrepresentation in low latitudes and high latitudes. So we don't have the tropics covered. We don't have Antarctica or the Arctic well covered either. And as you can see, most of them are over land areas, very few over the oceans. So they are biased spatially as well. Now, in the United States, we have two types of networks that we use primarily. One is the National Weather Service 8-inch rain gauge, which you can see is a design that's about this high above ground. You can see that it's designed that way so an observer can come around every hour, take the top off, look in, take the approved National Weather Service dipstick, measure the amount of precipitation, pour it out, and set it again for another hour measurement. The one on the right is a cooperative network. These are measured about once a day. And so these are all over the place. Farmers and so forth will get one. I brought one just for fun because I had nothing else to do. So here it is, and now I can count it off on my taxes. But in any event, there's about 13,000 rain gauges associated with the conterminous United States. And if we pretend that about 3/4 of them are the co-op, that is a 5-inch gauge orifice, and about 1/4 of the National Weather Service 8-inch gauge orifice, the question is, how much area are we really covering in terms of rain gauges in the United States? So we can say that the 5-inch orifice diameter is about 19.63 square inches. The 8-inch is about 50.27 square inches. We can do our multiplication, which is left as an exercise for the student. And you can see the total area that's covered is about, not quite, 2,500 square feet. Compare that, for example, with a soccer penalty area, which is just under 10,000 square feet, a Major League Baseball diamond between the 4 bases, which is 8,100 square feet, the National Football League football end zone, which is 4,800 square feet, an NBA basketball court, which is 4,700 feet, or between the NHL blue lines, I think I've got every sport necessary, and it's 4,250. So you can see, next time you're watching a sporting event, realize that the field or area on which, pitch, whatever, rink, on which the people are playing is actually much larger than the area in the United States that we actually measure rainfall. And remember, the United States has a lot more measurements than most other countries as well, much denser network. Now, you might think that the biggest enemy of a rain gauge is, in fact, birds. And we've done all sorts of things to try to keep birds from sitting on the edge for obvious reasons. But that's not really the biggest problem that we run into. In fact, the biggest problem is not sighting. And in fact, some of these sighting characteristics, I would argue, are probably better than the way we actually really do it. And the problem is, it's the effect of wind. Wind on a precipitation gauge, again, we're trying to measure mass. So as wind encounters the can-type rain gauge on the left, you can see 2 things happen. 3 things happen. One is, as the air hits the gauge, it's forced to flow up and over the top of the gauge, which gives you a slight updraft that takes place. Secondly, there's a compression of the wind field, so the wind moves a little bit faster across the orifice. And third, there's a pressure differential between the air at rest inside the can and the air in motion above it. And all of this means that the precipitation is going to be underestimated. It's underestimated quite a bit with rainfall, but really dramatically with snowfall. So what are we to do? Well, one thing we can do is put these in the ground. And in fact, you can see some places do that. These are pit gauges, as they're called, but no operational group likes to deal with them because imagine trying to get in there every hour and take a measurement. It's just not, you would like it right up here where you are. So what they do is they put some form of shield on it. In this case, you've got a knife or shield. Uh-oh, he's coming towards me. Okay, sorry, I thought you were gonna, anyway. So you can see there's a knife or shield, and the idea with a shield is so that it separates the air above from the air below the orifice of the gauge. So you don't have this compression of the wind field, you don't have updrafts, and it works fairly well. And you can see that snowfall with a shield and rainfall with a shield are better, not perfect, but they're better than what they were when we just had simple rainfall or snowfall. Here's a knife or windshield. The Canadians used quite a bit. They were originally designed in copper, and then they found out people were stealing them. So they made them out of aluminum, and apparently people don't steal them now, although I don't know why. Aluminum sells well, but nevertheless, aluminum doesn't get stolen. But there's other designs. The Soviet Union, they came up with the Tretyakov shield, which are fixed slats, and they have the same effect. And in the United States, we have the Alter shield, which is sort of movable slats. And they both do the same thing. And you can see here is a Tretyakov windshield in the wild, as they say, and an Alter windshield that we use in the United States. Second problem, not just wind, is wetting on the internal walls of the gauge. The idea is that that water sitting on the internal walls of the gauge should have been counted as precipitation. Never made it inside the rain gauge itself. So there's a wetting loss from the water that adheres to the outer side of the gauge. That's a problem. And the third problem is, particularly with cooperative gauges where you're only coming out once a day, they tend to evaporate. And that's why we have an evaporation pan. And you can sort of see, if you squint a little bit, that a rain gauge is really just a type of evaporation pan, except we're not really measuring evaporation. We're getting evaporation, unfortunately, as a byproduct. So what I found with a global assessment is that globally, precipitation is measured precipitation is an underestimate of the exact actual rain that falls, about 8% due to the effect of wind, 2% due to wetting losses globally, and evaporation losses about 1%, which gives us an undercatch of about 11%. The other thing you'll notice is the logarithmic wind profile, which you may be familiar with. The idea is the higher above ground, the higher the wind speed. The higher the wind speed, the greater the loss of the catch. So the problem is, if you have a gauge higher above ground, it's going to be subject to faster winds. It's going to have less of a catch than if we were to put the gauge down to the ground, which is one of the ideas of putting a pit gauge into the ground and burying it. Now, this is a conference on climate change. I have just gone 9.5 minutes, and I haven't mentioned the word climate change or global warming or anything like that, but I would be remiss if I didn't. Now, this is where the problem always starts, because here you can see the Times comes up with an article that says, extreme rain and flooding will rise due to climate change, study says. Heavy rainfall events will be 4 times more likely in 50 years' time, putting homes and businesses at risk. And the argument is for 2 reasons. One, climate model, I've been told this time and time again. Climate models say this is true. That must make it true. Secondly, I'm told that what happens is with these data is that the Clausius-Clapeyron relationship means that as temperature goes up, you get more water in the atmosphere, and therefore it stands to reason that when you get condensation, then the precipitation falling out of it is going to be greater, and so we should get heavier rainfall rates. So it stands to reason warmer temperatures, and because the models say it has to be this way, that we should be seeing an increase in precipitation over time, and indeed they'll show you a graph like this. This comes from NOAA's Climate Extremes Index, and this is, as you can see, the extreme one-day precipitation event. So I went back and I got the current data, and you can see here it is in points. And they plot a moving average, and sometimes I've seen it plotted like this, and then truncated off at about 1950, so you see a nice rise. And yes, in fact, that's rising, and that fits perfectly well with the carbon dioxide curve, and therefore greenhouse gases must be inducing this increased precipitation because, again, the models tell us so, and because it has to fit the Clausius-Clapeyron relationship. But I'll tell you, I took one look at that and I laughed because I know what's going on, and you may know what's going on. And if you don't, I will show it to you because it's one of those things, once you see it, you can never unsee it. So here's what happens. What are we looking at, first of all? On the left axis, we have percentage of the United States with a greater than normal proportion of precipitation derived from extreme one-day precipitation events. And this is equivalent to the highest 10th percentile. So you take all of the data, you figure out what are the heaviest 10% of rain days, and you say, are we getting more of our rain from the station? If so, we count the station. If not, we don't. We do that for each year. We found out how many stations we have. And our expected value should be 10% because on average, we've got the highest 10th percentile, so this should average out to 10%. And again, you can see that it's a little bit lower and a little bit higher. But what I know is the following. Through 1990, we used the standard National Weather Service rain gauge. It's located about this high, subject to wind effects, has a person every hour comes out, takes a dipstick measurement. So there's wetting losses, there's evaporative losses too. But the National Weather Service in about the early 1990s said, why are we wasting this? This is bad use of our manpower. What we really want to do is we want to upgrade to more electronic means. So what they decided to do was to get rid of these and change it with what's called the ASOS gauge. ASOS is Automated Surface Observing System Rain Gauge, which is a tipping bucket gauge. The way the tipping bucket gauges work, you can see there's a little, I don't have a pointer, but there's a little tipping bucket that goes back and forth. Every 1/100th of an inch of precipitation causes the bucket to tip. There's a little reed switch that measures it. We get a real-time measurement of how much precipitation is falling when that reed switch tips. We don't have to wait for an hour, or worse yet with the co-op data, we don't have to wait for the end of the day to figure out a daily average. You know exactly when that rain fell. We can do sub-hourly values. Makes lots of sense. So the idea then was we put these out at all of our first order weather stations. And now you can see here is one. It is much closer to the ground. We don't need to have people out there every hour. We just need a technician to come out every month or so to make sure it's working right, lube it up and so forth. And so it can be much closer to the ground, which it is. Well, remember, closer to the ground, lower wind speeds. Lower wind speeds, it's going to have an increased catch. Then we do the second thing, and that is put a windshield on it. So now we're going to get a much more efficient catch to this gauge than we were getting with the 8-inch orifice gauge sitting at this height. So there's going to be a discontinuity in the record driven by simply changing instrumentation from the National Weather Service standard 8-inch gauge to the tipping bucket gauge. The original design was to heat these things up really hot so that when snow or ice fell on it, they would melt. And you would just measure it just like you did with rainfall. The problem is it didn't work well at all. It started to evaporate, and there were all sorts of correction equations that said, you know, you got to cover up 30, 40, 80% of the precipitation that fell. So we now use these kind of things to measure snowfall. But snowfall is not usually the heavy rainfall events, not the heavy precipitation events. And so as a result, we're not really going to be concerned with these. It's really the tipping bucket gauge that's going to be controlling that previous curve. So let me go back to the data. Now, do you see it? If you don't see it, I'll help you out a little bit. Here you can see the pre-National Weather Service modernization data up until 1990, and you can see that curve is as flat as a pancake. I mean, at that R squared level, I couldn't get an R squared that low if I took a random number generator. Okay, so there has been no trend in this data from 1910 to 1990. Then if we go after the National Weather Service, the post-modernization, and we plot, you get another flat curve with no trend. But what happened? There's a jump discontinuity in here because we have a more efficient rain gauge. And because we have a more efficient rain gauge, that has increased that number by a little over 4.5%. So what you're seeing in the record is not a climate change signal that we could attach to greenhouse gases. What you're really seeing is a problem associated with gauge measurements. And that was the problem trying to come up with a global estimate of precipitation, was how do we do that kind of stuff? And because we've got gauges here, gauges there, and now worse yet, within a country, we've got changes that are taking place that makes it look like there's a climate change signal when in reality there isn't. The study goes a little bit deeper. It says, well, notice in the Northeast, that's your biggest difference between the pre and the post National Weather Service modernization. What's going on in the Northeast? Well, it turns out the Northeast has a higher number of National Weather Service gauges. So ASOS appears much more frequently up there. The gauge change is dramatic. And you can see for the Northeast region, the difference has been a change of 10%. But they also notice, mainly National Weather Service gauges. They also notice down here in the Northern Rockies and Plains, the Southwest region, the West region, and the Northwest region, these numbers are fairly low. Well, if you read the fine print, what they tell you about this index is that in these regions, there weren't many National Weather Service gauges. So they took a lot of the cooperative network and added them in. Remember, the cooperative network didn't change. We still use that same type of design, and we still use it today. So those numbers should be lower because we've got gauges that didn't change adding to the numbers, and that's why they're low. So these have been augmented with cooperative gauges. Now, back to my home state of Delaware and home of, Joe Biden, you know. In December, we came out with the Delaware Climate Action Plan. This is a 288-page of what we're going to do to stop climate change in Delaware. And you know, if we stop, we're going to be net zero by 2050. And when we do, you know how big of an impact that's going to have on the global air temperature record. Well, it's going to have a big impact on the precipitation record too, because if you read it, it says, since 1895, Delaware's annual total precipitation has increased by about 3 inches a year and is projected to increase by another 2 to 4 inches per year. Somebody needs to read this stuff before they publish it. It's not per year, it's over the whole bloody record. So it went from like 42 to 45 over that period. But this thing is a playbook. It's got all sorts of kitchen sink type of things to change and how we're going to be net zero. And any event, it's available online. But what I did was I went back to the data. Let me go back one step. This is from total precipitation from source NOAA's Climate at a Glance. So I went to NOAA's Climate at a Glance, and here are the data. And I decided, let me try the same thing. What happened in 1990? So I looked at this. This is the pre-National Weather Service modernization. There's your post-National Weather Service modernization, and there's a discontinuity that occurs right there. It's the change in gauge network that creates virtually every bit of that signal. It's not a climate change signal that you would even believe immediately would have anything to do with carbon dioxide or with greenhouse gases, because it doesn't wind up as a jump discontinuity. It winds up as a trend, if it were doing that. But you can see here that it's simply a jump discontinuity because of the gauge change. Except every time I've tried to publish this, the reviewers come back and say, you have to be wrong because the models say precipitation should be increasing. And after all, go back to an introductory text, read the Clausius-Clapeyron relationship. You'll understand why you did something wrong. I don't know what it was, but you did something wrong in there. I didn't, trust me. And fitting a line like that is the most ridiculous thing we can do. But then again, we did that in Delaware and are going to do that. Thank you very much.